While the comparison test is very useful, you do have to show the inequality, and you do have to prove that the inequality with your comparison series holds in order to use it. And sometimes that can be difficult or even impossible. So we have a modified version. And this is known as the limit comparison test. To start with, we need two series that I'm going to denote by the sum of AK and the sum of BK. And our series need to have positive terms. I'm going to denote the limit as k goes to infinity of a sub k over b sub k to be equal to L. And this is what we're going to be looking at with the limit comparison test. And then there are three things that could happen in this limit comparison test. The first one, if 0 is less than L is less than infinity. So this limit is a positive finite number. Then either both of my series converge or both of them diverge. So if I get a positive finite number here, and then I know something about b sub k, my comparison series, if the summation of b k converges, then I can say my other series converges, and if it diverges, I can say the other given series diverges. The second case, if L is equal to 0 and I know my comparison series converges, then the original series also converges. And then the third case, if this limit is equal to infinity and my comparison series diverges, then my original series must also diverge. So you'll notice if this limit is 0 and the comparison series diverges, I won't be able to say anything. And if the limit's infinite and the comparison series converges, I won't be able to say anything. So there are cases where this might not work. But let's look at some examples. Here's my first example. I have the summation from k equal to 1 to infinity of k cubed plus 4k minus 2 over 3k to the fifth plus k minus 1. So the first step is to figure out my comparison series. And what I'm really concerned with when I figure out my comparison series are the terms with the biggest exponents, the leading terms. And the coefficients of those terms really aren't going to make any difference in the problem. So I'm just going to deal with k cubed over k to the fifth, the two things with the highest exponents. And we can see that's the same thing as just the summation of 1 over k squared, which we know by our p-series test converges. So now let's look at limit comparison. We're looking at the limit as k goes to infinity of the first series that we had, the original series, divided by b sub k, divided by my comparison series. We should recall that whenever you divide by a fraction, it's the same thing as multiplying by the reciprocal. So it's the same thing as multiplying by k squared over 1. Once we multiply that out, we get the limit as k goes to infinity of k to the fifth plus 4k cubed minus 2k squared, all divided by 3k to the fifth plus k minus 1. Now it's important to remember that whenever we're dealing with limits, we really only care about the leading terms. So this will be the same thing as the limit as k goes to infinity of k to the fifth over 3k to the fifth, which is equal to 1/3. So I now have my limit. My limit is 1/3. And the first part of my limit comparison test said that if I get a number that's between 0 and infinity, so a positive finite number, which this is, then either both series converges or both diverge. We already know our comparison series converges. So that tells us that our original series must also converge. Let's look at another example. I'm now looking at the summation from k equal to 1 to infinity of k over k squared plus 3. When I look at my comparison, I only consider the terms with the highest powers. So I'm only considering the sum of k over k squared, which is the same thing as the summation of 1 over k. And we know that the summation of 1 over k diverges by our p-series test. So now let's start looking at our limit. we need the limit as k goes to infinity of the original series divided by the comparison series. And just like before, whenever you divide by a fraction, it's the same thing as multiplying by the reciprocal. We can then multiply that out, which is the limit as k goes to infinity of k squared over k squared plus 3. And using our rules for limits, we get that this is equal to 1. Since this is a positive finite number, we know that either both series converge or both diverge. I already know my comparison series diverges, so my original series must also diverge. Let's look at one more. I'm now looking at the summation from k equal to 1 to infinity of ln of k over k squared. It might be harder to figure out what we want our comparison series to be here. Let's start with just 1 over k squared. And we know that that converges by our p-series test. So now let's start looking at the limit. We need to take the limit as k goes to infinity of the original series divided by this comparison series. And I went ahead and wrote this as the multiplication by the reciprocal. When we multiply this out, we get the limit as k goes to infinity of ln of k, which we know is infinite. The limit comparison series test specifically said if the limit's infinity and the comparison test diverges, which is not the case here. So this is actually inconclusive. So maybe we should try to pick a different comparison series. This time I'm going to use the summation of 1 over k, which we know diverges. It's common to use the fact that ln of k is less than k. So maybe by using k for the top and k squared for the bottom, we can get something that works a little bit better for us. We then need the limit as k goes to infinity of the original series divided by the comparison series, which I went ahead and wrote as the multiplication. So that gives us the limit as k goes to infinity of ln of k over k, which is 0. And if you don't quite believe me this is 0, you should try it yourself. You would need L'Hopital's rule to actually figure out this limit, but it is actually equal to 0. So our limit comparison test said if the limit's 0 and the comparison series converges, which isn't the case here. So once again, we've picked something that didn't work. So let's try one more time. The first time I used 1 over k squared, and then I used 1 over k, so this time I'm going to go directly in the middle and look at the summation of 1 over k to the 3 halves, which by p-series does converge. So once again, we take the limit as k goes to infinity of the original series divided by the comparison series, and once again I went ahead and wrote that as the multiplication by the reciprocal. Multiplying that out gives us the limit as k goes to infinity of ln of k over k to the 1/2. Which, once again, I encourage you to use L'Hopital's rule and double check, but you should get that this limit is equal to 0. So once again, our limit comparison test said if the limit's 0, which it is, and the comparison series converges, which it does, then the original series also converges.